Now, two other properties that are important to know about waves are wavelength and frequency. Wavelength can be defined a couple different ways, but I think the easiest way to think of it as the peak-to-peak distance. So it's going to have the same units the distance has. If you look at the wave, this is the distance that it's propagating along. So the SI units of wavelength would be meters. Now very often when we talk about electromagnetic radiation, we use wavelengths that are much smaller than that. When we talk about infrared radiation, we use micrometers. When we talk about visible light, we use hundreds of nanometers for that. And if you're talking about gamma rays and X-rays, you might use picometers for your wavelengths. So they'll use different SI prefixes to adjust the units that they're reporting their wavelengths in. Now, it has a symbol that I drew up there. A lambda is a shorthand way to write wavelength. It's a Greek letter. Lowercase. Lambda. Okay. So there's another way I guess you can think of the wavelength. You can think of it not just as the peak-to-peak distance. You could think of it as the distance for a complete cycle. So here I start the wave, say, and I go through a complete cycle by there. So the wavelength would also be this distance. It's the same thing. The distance for a complete cycle is the same distance as the peak-to-peak distance. So that's fine. I mean, you could also say it was the trough-to-trough distance is the wavelength. So you're free to think of it in any one of those ways. Now, wavelength is kind of important because it determines in electromagnetic radiation, the wavelength of it determines the color of the light. So when you change the wavelength, if it's electromagnetic radiation, you change its color. How does that work? Well, let's see. If you've got violet light, your wavelength is going to be about, here, let me move this a little bit. If you've got violet light, your wavelength is going to be about 400 nanometers. If you've got red light, your wavelength is going to be about 700 nanometers. And you probably know from grade school that you can have all kinds of colors between there. After violet, you can have blue, and then you can have green, right? And then you can have yellow, and I don't have a yellow pen. Then you can have orange, and then red. So you get red, orange, yellow, green, blue, and violet, and that makes the visible spectrum. You call that wavelength range the visible spectrum. Now, I would kind of like you to know what the wavelengths are for the borderline, the borders of the visible range. You can't really see any radiation that has a longer wavelength than that. Well, There are some women that can see that. Because of that double X chromosome thing that women have, they have the ability to see what they call 2-photon hits. And that means that some women can see colors up into the infrared. And they probably are not aware of it. Maybe you're one of these people. If you're a guy, don't even bother trying this because you can't see up into the infrared here. But if you're female, go and get a TV remote which has an infrared LED on it. And go into a closet and click the remote. And if you can see the LED light, you're actually seeing some infrared radiation, and you're one of the people who can see into the infrared a little bit. Now, not all women can do that, but there are a few who can see these colors. And probably your color perception is quite a bit different from other people's color perception too, if you're one of those people. And they're not that common, so go check that out. But most people, most humans, can only see between 400 nanometers and 700 nanometers. If you look at colors that have longer wavelengths, this might be what we call the infrared region of the spectrum. And up above that, at longer and longer wavelengths, you can have microwaves. And up at the very longest wavelengths there, you can have radio. So the only difference between this stuff and visible light is just the wavelength is longer than 700 nanometers for all of this. Microwaves have a longer wavelength than infrared, and radio has a longer wavelength than microwaves do. Now, down on the other end of the spectrum, off the visible end, when you go past violet, you can probably guess what that's called. That's the ultraviolet. And you can't see down there, but your cat can, and insects can see down there. And a lot of the colors of flowers are colors that we can't see down in the infrared, the ultraviolet region. Sorry. Some flowers look like little targets when you look at them with an ultraviolet light. And that's to guide the insect to the center of the flower. So flowers were made for them, not for us. And if you go to shorter wavelengths than that, you can get down to X-rays. And you can get down to that kind of radiation that we talked about in Chapter 2, gamma rays. They're very short wavelengths, very tiny wavelengths. And those are two kinds of radiation that have shorter wavelength than the ultraviolet even. So very short wavelengths, longer, 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 even longer. You know, that's the way it goes. I'd like you to remember these in order. You don't have to remember what the wavelengths are for gamma rays or X-rays or ultraviolet, but you should remember that this is the order that they go in. There's three that I want you to remember that have shorter wavelengths than visible light, and there are three that I want you to remember that have wavelengths that are longer than visible light, and I want you to know where the borderline is for radiation that you can see. Okay, so that's wavelength. What about frequency? Frequency has to do with both wavelength and speed. If I have a wave that looks like this, and it's moving by me at the speed of light, and I have another wave that's moving by me like this, and it's also moving by at the speed of light, and I'm counting how many peaks pass by per second. I'm going to get a lot of peaks per second here, and I'm going to get only a few peaks per second here. Peaks per second is frequency. You can say, instead of peaks per second, you can say cycles per second if you like, a complete cycle being a peak and a trough going by. Same thing. Peaks per second or cycles per second, same thing. Now, this one would be a high frequency. And I'm going to write a little symbol here. And this one would be a low frequency. Now, let's sort all this out. Frequency. Let me use a different pen. So what are its units going to be? Well, peaks is just a count, and it's not really a unit. So that you can say that the units are going to be 1 over seconds. Those are the units of frequency. And you can write that a different way. You can write that as seconds to the -1. Since 1 over x is x to the -1, you can write the units as seconds to the -1 too. You can say that as reciprocal seconds if you want. This unit has a name. It's called a hertz, after a radio pioneer named Hertz. And the abbreviation for it is capital H, lowercase z, the abbreviation for Hertz. If you look at the radio dial in your car, you'll see that it'll give frequencies on the dial for different stations. And it'll be in megahertz, the capital M for mega, your SI prefix. So that's millions of cycles per second or millions of peaks per second that you're getting with that particular radio radiation. Now, how is frequency related to wavelength? Because they're not independent from that picture that we drew before. We said this is high frequency. And I'm using this Greek letter here to say frequency. I'll draw it a little bit bigger. This is a Greek letter nu. And that's the symbol that they use for frequency. So there's a high frequency wave, and it's got low wavelength. Why? Because the peaks are close together, so the wavelength isn't big. Now if you have a wave that looks like this would be a wave with high wavelength and low frequency. And if you wanted to bring amplitude into that, you could look at how high the amplitude is, how high the peak heights were. So you could classify waves as high frequency or low frequency, high amplitude or low amplitude, by looking at what the wave looks like. Comparatively, this is a higher frequency than this one. This is a smaller wavelength than this one. Okay, so there's some kind of relationship here between wavelength and frequency, and you can't just change one arbitrarily and not change the other. What is that wavelength between frequency? What is that relationship between frequency and wavelength? Let's write down the units of wavelength. The SI units are meters. And let's write down the units of frequency. The SI units are 1 over seconds, or hertz. Now what happens when you multiply those units together? Meters times 1 over seconds. You're going to get meters per second, which is a speed. Distance per time is a speed. And in fact, this is a justification for this equation that I'm going to write. Wavelength times frequency is equal to the speed. And I'm using that for speed. And if we're talking about electromagnetic radiation, then that's going to be the speed of light. it'll be a constant. 2.9979 times 10 to the 8 meters per second. Now, here's the equation. Let's write it again. I'm going to put a box around this because this is important to memorize. You need to know this. We're going to use it quite a lot. Actually, we're going to use it in our lab that goes with lesson 3.2, the next lesson. Now, you can use this equation to calculate a frequency from a wavelength. If you get any two of the things in this equation, you can calculate the third thing. If I wanted to do an experiment that measured the speed of light, I could experimentally measure the wavelength and experimentally measure the frequency. And when I multiplied those things together, that would give me the speed of light. And that's one way to do it. Let's suppose I have a problem where I want to calculate a frequency from a wavelength, and I'm giving you a problem like that under this video. How would you do it with this equation? Suppose I have, I don't know, hydrogen emits radiation that has a wavelength of 656 nanometers. So suppose I know my wavelength, and I want to know what's my frequency in hertz. How many hertz are in 656 nanometers? Now, this isn't just a straightforward unit conversion. I have a little bit of algebra to do. I can write this down as a roadmap, though. I am trying to get a frequency in hertz. And I have a wavelength in nanometers. Now, I'm not going to write like just something equals something with units this time. But what I can do is I can say frequency. What's the connection between frequency and wavelength? And the connection is that equation. This connects these two things. But how I set it up will be a little different. I'm not going to have conversion factors. What I really want to do when I have an equation in here is solve this equation for my unknown. Here's my unknown. And solving an equation for an unknown is just another way to say I want to get the frequency, the nu, all by itself on one side. So what I'm going to try to do is solve this equation for nu. What do I have to do? I have to get rid of this lambda that's sitting next to the nu so I can get the nu all by itself. So what I'm going to do is I'm going to divide both sides of this equation by lambda. And now I have turned it into an equation for my unknown. I've solved this equation. Now, to get the answer, I have to plug in the numbers. Now, speed of light I have to look up. You don't have to remember this number. You'll always be able to look it up. But it's the speed of light. That's the c that goes on the top. Now how about the lambda? Okay, if I naively go and type this into my calculator, I will get the wrong answer. If I try to do 2.9979 E8 divided by 656, I'm not going to get the right answer. Can you spot what the problem is? If you said that the units are not going to cancel out to give me frequency units, that's right. You can always tell whether you've got this solved equation set up right because we know what the units ought to come out to be. They ought to be hertz, and that's 1 over seconds. And that means that these length units that I have here have to cancel out. And since they're different, they're not canceling out. What I need to do to solve this and get a number that has the correct units is I have to convert the units so that they're both the same and so that they'll cancel out. Now it's easy to do for me without a lot of fuss because I know what nano means. Nano means times 10 to the minus 9. And instead of having nano there, I'm going to just erase the end and put what nano means, times 10 to the minus 9. Now look what happens. The meters will cancel out, and I'll be left with 1 over seconds, which is the same thing as hertz, which is the units that I'm after. So if I type it in, I'm going to type in 2.9979 EE 8. There's my speed of light divided by 656 EE minus 9. I'm using the sign change key there for that. Now notice I didn't put that in scientific notation first. I mean, I would have to bump the decimal point over 2 places and write 6.56 times 10 to the minus 7 to have this bottom number in scientific notation, but I don't care. I just typed it in like that, and the calculator recognizes that that's the same number that I would have had if I put it in scientific notation. So you can save yourself a little bit of work. You're only interested in the answer. You don't have to put everything into proper scientific notation unless you're showing it to another person. Now if I say equals, I should get my answer. And it is 4.569969512 times 10 to the 14 hertz. I can say 1 over seconds, or I can say hertz. Same thing. Those both mean the same thing. That's Hz, not H2. All right, what about significant digits? How many significant digits should I round this off to before I show it to anybody? Well, this has 3, and then this had 5. So this is my weak link. 3 significant digits is what I should round this off to. So here's where my cut's going to be. That's bigger than a 5, so I should round up. So I should write 4.57 times 10 to the 14 hertz is my answer. Now there's a problem just like this below.